1. Alright, for this next experiment, we're going to use some zinc metal, and we're going to mix the zinc metal solid here with some hydrochloric acid. So the concentration of the hydrochloric acid we'll be using is 3 molars. So what we're going to do is that we're going to put some of the zinc metal and we're going to put it into the balloon. So you want to have really small pieces because you want to increase the surface area and you want it to react faster. If you have really big chunks of zinc, then your reaction will still occur, but it will just take a little bit more time. So now I'm just going to try to stuff this balloon with a little bit more zinc. Trying to put as many little pieces as possible. And once you have once you have the zinc into the balloon, then you need to put your hydrochloric acid. I think I have enough here. Put some of your hydrochloric acid into your Erlenmeyer flask. So I'm just going to pour a little bit. I would say roughly about 50 to 70 millimeters, depending on how much of the zinc that you use. And the second step of this is going to try to put this balloon over the mouth of your Erlenmeyer flask. And once you have it over, then you're going to empty your zinc metal into the flask. Alright, so the question here is that this is a single displacement reaction. So we have HCl plus zinc in a single displacement reaction. So what do you think the products will be? So after 5 minutes or even more, if you want to wait a little bit more just to get the balloon a little bit bigger, that's fine. But this is after 5 minutes. You can see the balloon has inflated quite a bit. Again, this is a single displacement reaction, so you can see that this reaction actually gives you H2, which is a hydrogen gas, and zinc chloride. So the zinc chloride is actually still in solution. What's collected here is going to be your hydrogen gas. So how can we test this hydrogen gas? Well, first I'm going to try to take this off and put this into the fume hood, and I'm going to tie this up. So to test this, because I know the properties of hydrogen gas, I'm going to move all this stuff out of the way. I'm actually going to light it and put it into open flame. So I'm going to take this balloon. This is very important because you do not want to hold this balloon over the open flame because that's very dangerous. So I'm going to put this at the end of a meter stick. I'm just going to tape it down. And move the tape out of the way. And here's my candle. I'm going to light the candle. And now I'm going to put the balloon over the candle, over the open flame. If it is hydrogen gas, you should see a pretty strong reaction. Alright, so I'm going to put this over the candle. Woo. And there you go, a single displacement reaction.
When you look at the periodic table in group 17, you see fluorine, chlorine, bromine, and iodine. And what we want to look at is, what is the periodic trend of activity? In other words, which is more reactive? What we're going to do is we're going to compare the chemistry of what will replace what by putting these compounds in a sequence of solutions. In each of the test tubes, we have cyclohexane. And in the first one, I'm going to add potassium fluoride. And you can see that we have 2 levels in our test tube. The solution of potassium fluoride is in the bottom and the cyclohexane is at the top. In the second one, we're going to put the chloride ion. See the same thing happen. And the bromide ion. And in this one we're going to put an iodine ion. Now we have fluorine, chlorine, bromine, and iodine. And what I'm going to do is to add a solution of bleach. This is household bleach. and there's chlorine gas in here, and it will come out of solution. So what we want to do is to see if chlorine will replace the fluorine, bromine, or iodine. From this we can see that chlorine does not replace the fluoride, but chlorine does replace the bromide and the iodide. This time we're going to add just a little bit of bromine in a water solution. So we have bromine as a compound. What we see here is that the bromine did not replace the fluoride, the chloride, or the bromide, but it did push the iodide out of solution. And so you can see iodine down in the bottom.
In this video, we're going to identify and state chemical equations for single displacement reactions. So how do we visualize that? Well, we can see here a compound plus an element is making a new compound plus another element. And what you can kind of see here is that the B and the C swapped places, and that's what we call single displacement. One displaced the other or replaced the other. Sometimes we call them single replacement reactions. So one element is replaced by another in a compound. So we identify that as compound plus element gives compound plus element. Now let's take a look at an example. So here's sodium chloride, and it's being reacted with potassium. And what we note here is that potassium is a metal. So the metal is going to compete for the nonmetal, which is chlorine. So sodium and potassium have to duke it out and see which one gets chlorine. And in this case, potassium ends up winning and it combines with chlorine, and then sodium is off on its own. In this example here, we have fluorine coming in, and this is a nonmetal. So the nonmetal is going to compete with the other nonmetal, which is chlorine, for sodium. So in this case, we see that fluorine beats out chlorine, and we end up with sodium fluoride, and chlorine is off on its own. Let's talk about how do we actually predict these. There's a few steps that we go through in order to do this. So let's start with an example here with metal and metal challengers. So like the one we talked about on the first page. The first step we need to do is we need to look at the reactants and decide if the metal or the nonmetal is trying to do the replacing. So you have to look at the element that's on its own and see what does it want to replace. If it's a metal, it wants to replace the other metal so that it can be with a nonmetal and create an ionic compound. So once we've decided that it's metals, the next thing we need to do is we need to compare these two metals on the table to decide which one is more reactive. So here we have a table called the Reactivity Series. And how it's arranged is the more reactive metal is at the top. So you can sort of think of these as like wrestlers that are ranked. The strongest wrestlers are at the top and the weakest ones are at the bottom. So in this case, we have sodium and potassium. So we have to find those on here. So sodium and potassium. And we have to see which one is stronger. Well, potassium is stronger because it's higher up, it's more reactive. So potassium is strong enough to take away the chlorine from sodium. So it's going to do that. So when it does that, we have to think about what compound will it form. Well, potassium, we have to do our crisscross because that'll be ionic. It's metal and non-metal. So our potassium is in group 1, so it forms a K+, and our chloride is in group 7. It's going to make a Cl-. And so we crisscross and we figure out, okay, it's going to be KCl. It's ionic, so it's solid. And then our leftover will be sodium. Then we can balance that. We can see here that it's already balanced. Now let's do another example here with some metals. Let's this time do sodium chloride with aluminum. So here again we have a metal, so we have aluminum challenging sodium for the chlorine. So we take a look at our table here and we compare aluminum and sodium. So sodium is stronger than aluminum. So aluminum is not actually strong enough to take away this chlorine from sodium. So what actually ends up happening because of that, is no reaction. So the way we signify that is by writing an X over the arrow and then just writing no reaction. Now let's do one for nonmetals. So here we have sodium chloride again, but this time we're being challenged by a nonmetal. So this nonmetal is going to compete with this nonmetal to see which one can be with sodium. So in order to compare those and see if they're stronger, we have a second series for the halogens. So fluorine is more reactive than chlorine, which is more reactive than bromine, which is more reactive than iodine. And this is actually the order that they are in on the periodic table, so it makes them easier to remember. So here we have to think about, okay, is fluorine stronger than chlorine? Yeah, fluorine is stronger than chlorine. So fluorine will take away the sodium from the chlorine. So we have to think about, okay, what will it make? So it's going to be ionic again. So sodium is in group 1. So we need to do the plus, and because it's in group 1, so it's going to form a +1 ion. Fluorine is in group 7. It's going to make the negative ion. So we crisscross, and it's going to make sodium fluoride, and then the chlorine is going to be left over. And again, we have to write chlorine as is found in nature. Now we have to balance, and we see that that all works out. Let's do another example of a nonmetal. So here we again have sodium chloride, but this time we're going to react it with bromine. So here again we have nonmetals competing with another nonmetal for the sodium. So we take a look and we compare. Okay, chlorine is stronger than bromine. So this bromine is not strong enough to take the sodium away from this chlorine. So as a result, there's going to be no reaction. So if you go through these 4 steps and you always refer to your table, then you'll be able to predict whether it happens or not. And then if it does happen, then you can predict the products with the crisscrossing. We're only going to be working with ionic compounds in these single displacement reactions.